Hello. This will be AP Chemistry Notes, pages 96 to 98. We're starting a new unit. It says that the chapters are 20 to 21, but they're actually more than that. Let me check the book. We'll actually be doing 20 and 21 will be this lesson. But then we're also going to do chapter 22, which is organic, and then we'll also do chapter 19, which is nuclear. So it's more like 19 to 21 is the unit, and this lesson is 20 and 21. Now, other than the nuclear section, there really won't be any calculations. So especially these two chapters, 20 and 21, you can refer to these as qualitative. In other words, it is not number-based, or at least not very much. So let's jump into this stuff. We've talked about this in the past. The transition metals often form colored compounds, like iron compounds, copper compounds, nickel compounds, cobalt, manganese, and so on. And it's because they have d electrons that are able to jump around within the d subshell. Now you'll notice I mentioned except zinc. Zinc compounds are white. They have d electrons, but it's full. So it's difficult for those electrons to jump around within a particular d subshell because it's full. And that explains some colors. For example, I've already said that zinc compounds are typically white, and group 1 and group 2 compounds are typically white because either they don't have any d electrons or their d is full. Whereas if you take a look at copper compounds are often blue or green. And then here in the case of manganese compounds, you see purple, green, brown, black, pink, and so on. It's because not only do copper and manganese have d electrons, but they're not full, and that's important. You'll see in the case of manganese, it makes a bunch of different colors based on its oxidation state. And I have a demo that I'll show you in class later that will show all of these, or at least most of them. Now, another thing regarding colors is what's known as a flame test. Now, the colors I mentioned before are just without any extra energy. So everything I mentioned before the flame test, that's just when you look at it and you're not really subjecting it to anything. A flame test, you're actually putting excessive energy in and you're causing the electrons to jump all over the place. And it could be useful when identifying things. So for example, I have some of the alkali metals listed here. And you'll see that lithium is red, so is strontium. Sodium's yellow. Potassium's kind of a violet. It's hard to see. It's like a violet pink, and it's typically difficult to see when you do a flame test because the flame itself is kind of bluish, and this often gets hidden. And cesium is blue, which is awful to try and see in a blue flame. But it is possible, like it'll intensify or change its hue. But I typically like to do lithium because it really stands out and is a really intense red color. Years ago, you used to have to memorize a bunch of different colors of things, but that's really not common anymore, so we don't need to go. All right, now, the rest of this lesson is pretty much going to be on reactions. So I am going to throw a lot of information at you, and it's going to take a while to get used to it. So give yourself some time. You'll have to look back at these notes a lot over the next few homeworks. So be ready for that. Let's start with some reactions that you should already know. Combustion, which of course is just some sort of fuel plus oxygen doing what it does. Sometimes it makes carbon dioxide and water, but not always. So be aware of that. Formation is when you have the elements and then they form some sort of compound. Precipitate, we studied that one in detail, is when you typically have aqueous ions, and then they form a solid. That one should be pretty familiar to you. Acid base, well, you have an acid and a base, and often they neutralize each other to form water, but not always, but that's a good starting point. And then redox we just did, and that's when you have some electrons being given by somebody and taken by somebody, hence the reduction and oxidation, which you should be very familiar with since we just did that unit. Now, in addition to these 5 that we've studied, there are what are known as the generic classification of reactions. And I have to say, I'm not a big fan of 2 of them. I am not a big fan of single replacement and double replacement. It's a fake pattern. When you look at it, it might look like these names fit, but I don't really believe they're a good representation of what's going on. So I'll show you why they're called that and why I'm not a fan of it. First, let's just go through the 5 names and where they come from, and then we can get into the weeds a little bit. Synthesis is just multiple things combining, hence the name synthesis. So you typically see multiple reactants and 1 product. Decomposition is the opposite. You see 1 reactant and multiple products, 2 or more. Single replacement is called that because it looks like something's being replaced. In this case, it looks like the hydrogen is being replaced by the zinc. Because notice the hydrogen's bonded to the chlorine on the left, and the zinc is, well, let me rephrase that. It's not bonded, it's affiliated with the chlorine on the left, and now zinc is affiliated on the right. Double replacement, it looks like the ions are switching partners. So we've got the sodium and chloride partnership, we've got the silver and nitrate partnership, and now it looks like the sodium and the nitrate are partnered and silver and the chloride are partnered. But let's finish this and I'll go into why I struggle with these 2 names. And then combustion, I already mentioned, fuel, oxygen, often forming CO2 and water, but not always. Sometimes instead, if there's not very much oxygen, you get carbon monoxide and water. And if there really isn't very much oxygen and things get really low, you get carbon and water because there's just not enough oxygen to go around. You often see that as soot. And we can talk about some examples of that in class. So I'm going to go back to my single and double replacement issue. If we take a look at the equation that I gave, it shows zinc solid and HCl. Well, it shows the HCl stuck together, but it isn't. If it's aqueous, otherwise known as hydrochloric acid, it's really this. And all that's happening, I go ahead and put states. Oh, by the way, this is an area you typically are going to want to put states on everything because they often matter. The hydrogen is becoming that. And the zinc is going to be losing electrons. So the zinc is becoming that. And the chloride is doing nothing. So really, it's not so much a single replacement reaction. Nothing's really being replaced. It's a redox reaction because of the electrons leaving the zinc and going to the hydrogen. And this chlorine, really, it was there, but it didn't really even do anything. So the way that it's shown in the equation as a single replacement, I find that actually to be misleading and borders on the line of being incorrect. But do be aware of the name single replacement. Double replacement, this one I think is even worse. if we analyze this one, we've got sodium chloride aqueous. Okay. Well, that really means this. This would actually be a better way to write it. And then we've got silver nitrate aqueous. So silver nitrate. And they're going to react. Well, again, the silver and the chloride are doing something. They're sticking together and they're making a solid. The sodium and the nitrate never did anything. They're not even needed. So saying it's a double replacement makes it look like they're switching partners, but they're not switching partners. It's just the silver and the chloride are choosing to become a partnership. So anyway, that's enough on that. Just be aware of it. Now let's classify these based on the types that I mentioned above, where I said combustion, formation, precipitate, acid, base, and redox. Realize that just because something fits one category doesn't mean it can't fit multiple categories. Like in the case of this first reaction, this is also a formation because it's elements becoming a compound. It's also combustion because magnesium's the fuel and oxygen's oxygen. It's also redox because if you look at the oxidation state, they're both 0 on the reactant side, and then on the product side, magnesium's +2 and oxygen's -2. So it fits into many categories: redox, combustion, formation, and synthesis. And you can look at it whichever of those you find the most useful. All right, now let's go to this second one, the decomposition. And we should go through what these are, by the way. You should recognize these 5 reactions and possibly even memorize them to use as an example in your toolbox. Let's go back to the first one. This is just magnesium and oxygen. This was a lab in first-year chemistry. You put a bunch of magnesium in a crucible, you heated it, and it reacted with oxygen in the air, and it turned into magnesium oxide. The second one, decomposition, this is just hydrogen peroxide decomposing. We talked about it quite a bit last unit. So it's decomposition, but it's also redox because the oxidation numbers are changing. And C, zinc and hydrochloric acid. This I use as a demo. If you replace zinc with magnesium, that was also a first-year lab, the one where you had magnesium and hydrochloric acid, you collected hydrogen gas in a tube. So you should be familiar with this one. It fits the single replacement definition and it also fits redox. D, which coincidentally kind of stands for double replacement. This, it's not redox. Of my 5 examples here, it's the only one that's not a redox. It is a precipitate. And I mentioned when teaching redox that precipitates are never redox. And then E is combustion. Oh, if I go back to the reaction, this is the famous precipitate, silver and chloride forming silver chloride solid. Sorry, I'm jumping around a lot here. For the combustion, it is methane, otherwise known as natural gas, or at least the majority of natural gas, burning in oxygen. So you know this as the Bunsen burner, or if you have a gas stove at home or a gas furnace, that's what they're doing as well. A very similar situation. This could be called combustion or redox. This one here, I'll mention in the next set. So these are just some generic things to be aware of. We've got the ones you should already know from past experience, and then the generic 5 that can be useful to help you. And now we're going to look at some specific ones, and you'll see I've grouped them to help you. So I've grouped A and B, I've grouped C and D, and there's more groupings lower on the page. So that's done on purpose to help you. A and B are very similar reactions. So let's start with A. If you put group 1 or group 2 metals in water, they react. Of course, group 1 in water is the famous demonstration. put sodium or potassium in water and it fizzes, maybe it catches on fire, and if you put too big a piece, it explodes. Well, what's happening here is a redox reaction between the metal and the water. The metal doesn't like being an oxidation state of 0, so it gives away electrons to become +1 in this case. Somebody has to take the electrons. The oxygen is already -2 in water, so it's the hydrogen that takes the electrons to become hydrogen gas here. And that's why if you put too much, it blows up, because you're making hydrogen gas and it's also exothermic. So too much, you're going to get an explosion. Now, by accident, you end up with a hydroxide. And I'll prove that. I'll do this same demonstration that you've already seen in class, but this time I'll do it with an acid-base indicator and you'll see it become basic. Rather than memorizing this, I think it's better if you just understand it. You know that a gas is made because of the possibility of explosion. It's got to be a flammable gas, so there's your hydrogen. If hydrogen comes from water, it has to gain electrons, so somebody had to lose electrons. That's the sodium, which is why it goes from Na to Na+. And then from last unit, you should know in this case, when water gets reduced, you're left with some hydroxide. So try to understand the reaction as opposed to just memorizing it, because that's no fun and not as helpful. Now, I haven't mentioned this before, but there's the special version of hydrogen called a hydride, in which the hydrogen is actually a -1 oxidation state. So if you look right here, lithium hydroxide, we know that lithium wants to be a +1. Well, that means in this case, the hydrogen must be a -1. So it actually has 2 electrons. And it's not very stable. It doesn't really like being this. So these are fairly reactive. And in this case, the hydrogen wants to get rid of that electron. Well, it's got 2 electrons, but it wants to get rid of at least one of them. So it's going to give them to water. If water gains electrons, just like before, you get H2. The lithium really isn't doing anything, and you're left with hydroxide. So notice these 2 reactions in A and B are very similar. So it's best to group those together. Next set, I put these 2 together because we've got metal oxides and non-metal oxides. Now, metal oxides, often when you put them in water, you form hydroxides. So I've got calcium oxide in water. Calcium stays an ion, and you end up with a hydroxide. Now, how you write this, you can write it, assuming it's in water, which it has to be because that's one of the reactants. You can write it as 2 separate ions because that's really what it is. Or if you really want to, I suppose you could write it like this. But that's not as good. It's better if you show them separate because that's what they really are. Of course, if it forms some sort of calcium hydroxide solid, then you would show it stuck together. So I'm going to recommend that you write it this way. Non-metal oxides often form acids. For example, if you bubble non-metal oxide gases through water, you often make acids that way. So carbon dioxide in water forms carbonic. You did something like sulfur dioxide and water, you would make sulfuric, or sulfurous, or something like that, aqueous, and so on. All right, ligands are back, but this time we're really going to get into what's going on. Now, when we first did ligands, we looked at a scenario like this, which was, how does a copper ion act acidically? Well, it gains water molecules to become the complex ion, and then that CuH2O4 +2 complex ion, it can give off a hydrogen from the water, and we did that 2 units ago. It turns out there are other ligands than water. So here's some common ones. We've got water, ammonia, cyanide, hydroxide, and or at least most of the halogens, are common ligands. And there are other more exotic ones. We'll see a few in homework, but for the most part, we'll stick to these ones. So in my example here, I just want to look at things that look like they could be a complex ion, and I want to go through why some are and some aren't. So this first one, that you should recognize as a hydrate. That is not a complex ion. This second one is a complex ion, and you should recognize that from the acid-base unit. You'll notice I put it in brackets to make it clear. You don't have to put it in brackets. You can write it like this. But the brackets are often used just for clarity, but you don't have to have that. So be aware, you might see something written like this. It's still a complex ion even without the brackets. Like the third example, that's just a precipitate. Fourth example, complex ion again. Partly because the brackets are telling you that, but also if you look at this, it's not what we normally see. So the fifth one, this one is a complex ion, and normally you would know this from a prior lab. You can see that I said that here, but we skipped the lab this year. It's the equilibrium lab, and you actually are doing the equilibrium of this complex ion. Hopefully we'll get to that later while we're reviewing for the AP exam. In future years that might be watching this video, hopefully you recognize this from the equilibrium lab, in which it was this complex ion, and it's in equilibrium with, if I remember right, Fe+3 and thiocyanate ions, and everything's in water. And that's the equilibrium system that we study in that lab. You'll notice in this case, I didn't double the ligands. If we followed the double the ligand rule, then it would actually have 6 SCNs stuck onto an Fe+3. We are going to follow the double the ligand rule, but there are cases where that doesn't apply. But we will mainly stick to this double the ligands just for clarity in our class. All right, next one, ligand substitution here. Turns out, if you have a complex ion, you can put in a new ligand that's more concentrated and it will take its place. So the more concentrated ligand can push the other one out. I don't have an example in the notes, but we will be looking at one later on. All right, carbonates and bicarbonates. Often, if you mix them with acids, they do what I refer to as the elementary school volcano. You get carbon dioxide, which causes bubbles. You're left with a positive metal ion and water. And I just remember carbonates and bicarbonates are the elementary volcano, which of course in elementary school you make the paper mache volcano and then you pour some baking soda into it. And then you pour some vinegar, which is your acid. And it then undergoes this reaction to make carbon dioxide. And it fizzes over. You probably put some red food coloring so it looks like lava, or at least tries to look like lava. And it's the greatest thing ever. Because you can't do things in elementary school with fire. So at that time, it's pretty cool. All right, next section. You don't need to worry about learning all of these. I just put them as examples. If all else fails, if you don't know what to do and you're stuck and you can't figure out what type of reaction something is, a good guess is synthesis. So if you're given more than one reactant and you don't know what to do and you're stuck, just stick it together. There's a good chance you'll be right. Next, heated stuff. If you heat stuff, and sometimes above the arrow, you'll see a little triangle, and that's what that means. The triangle represents heat. It's often decomposition. So carbonates If you heat them, they often break up, in this case, into carbon dioxide and a metallic oxide. So an example would be magnesium carbonate will form magnesium oxide and carbon dioxide. So if you see heated, it either means the reaction is going to go faster probably, or it's going to be decomposition if there's only one reaction. And the last chunk is we're going to look at 3 organic reactions. Now, there are so many organic reactions, that's a whole other class. If you major in science in college, you'll take a class or more in organic chemistry, and you will go through numerous reactions. It's really fascinating, but I'm only going to cover a couple easy ones right now. The first one's called addition, because you're just adding something to a molecule. In this case, we have ethene, and we'll go through some organic stuff next lesson. And we're adding a bromine molecule to it. So what's happening here is the ethene looks like this with 4 hydrogens. I'm not going to bother drawing. And you can think of the double bond as just opening up so that it does this. We still have our 4 hydrogens, but the double bond is now here with like a piece here and a piece here. And that's where the bromines attach. They attach here and here, or something like that. There's more than one possibility in this case, but that's the most likely one. Substitution, instead of just adding something, now we're actually going to take something away and substitute. And a very common example of this would be benzene, C6H6, and I'm adding bromine. But in this case, instead of the bromine simply attaching, a bromine from Br2 is going to switch with a hydrogen from the benzene. So if I draw a benzene molecule, carbon, 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 lots of them. That's a carbon, even though it doesn't look like it. There we go. And put in the 3 double bonds. There's also a hydrogen sticking off of each of these carbons, like so. That's benzene. In this case, you might think, well, shouldn't it do the same thing as letter A, addition? Turns out the double bonds in benzene are very stable, so they stay. Instead, what happens is you take one of these hydrogens and you get rid of it and you replace it with bromine. So that's where the bromine would be. You also make, in this case, HBr. You actually make a strong acid. You might think, wait a second, how can we be making a strong acid? You can't make strong acids in water. Well, we're not in water. We're in benzene, so it's okay. You can actually make a strong acid. This third organic reaction, esterification, or the formation of an ester, I'm going to study this in detail in our next, that'll be our next lesson. So I'm just going to save that one for there to not overcomplicate this lesson. All right, let's say after all of this stuff, you are given a couple reactants, or maybe one reactant, and you're asked, predict what the reaction is. It's going to be difficult at first because you have so many options, but with practice, you'll get better at it. Here are some suggestions. First, if it's aqueous, we don't need spectator ions. So you're welcome to write out everything that's in the reactants, but I recommend you cross stuff out or erase it. Let's just go down here. I'll show you what I mean. You'll see that in some of my examples, I have things written, but then I cross them out. That was because I realized they were a spectator ion, and then I crossed them out, and that's fine. So my recommendation is go ahead and write everything in your reactant side, and then cross out stuff that you don't need anymore. I actually don't want to look at too much of that right now. If it's a solid or a gas, go ahead and write the whole thing. Because that's how it exists. They're bonded together until they react. And I'm actually going to go back to letter A and reword that. If it says, if aqueous, write net ions only, well, you're eventually going to do that, but you might not even know what the reaction is yet. So I'm going to rewrite A to say, if aqueous, write as separate ions. I think that'll be better. And then we'll cross out them as needed. That's a better phrasing for that section. You do need to balance things, letter C. Usually we'll do lowest whole numbers. Obviously, if you use fractions or decimals, you're not wrong, but we won't match. So let's try to stick to lowest whole numbers so at least our answers match. I say states and letter D are optional, but they can be helpful. So if it seems like states are going to be important as you're reading the question, go ahead and put them. Worst case scenario, you decide you don't need them, you can ignore them or cross them out. Okay, let's take a look at some of these. Let's start with the first two here. Aqueous, and let me scoot this over a little. Aqueous sodium cyanide reacts with hydrochloric acid. So, since it says aqueous sodium cyanide, you should write sodium and cyanide. Hydrochloric acid, don't write HCl, that's not what it really is. HCl is really this. This is more useful to do it this way, and it's going to react. We have to figure out what it is. All right, so you have to go through all the options. Precipitate, redox, combustion, all the different things on the other page, the organic reactions, the elementary volcanoes. It's going to seem overwhelming, but in this case, well, we've got an acid. Okay, that's a start. And cyanide can be a base. All right, so it's acid base. The hydrogen and the cyanide will stick together to form the weak acid HCN. And notice, sodium and chloride aren't doing anything. So get rid of them, like so. And there it is. The second example right here is an identical acid-base reaction, but I want to show you why I included the sodium this time. This time it says solid sodium cyanide. So don't write it as separate ions. Write it like this, because that's how it actually exists. It's solid. The ions are stuck together. And then hydrochloric acid would be the same. Same reaction occurs. I'll just keep green, making HCN. But this time there was a change among the sodium. The sodium, it went from a +1 ion that was bonded to another ion in a solid. Now it changed state. So you could say that the sodium ion didn't really undergo a dramatic change, but it did change state. So it's best to show. And so I intentionally chose those first two to help you see that difference. All right, let's just go ahead and do a chunk of these now. All right, potassium oxide, K2O, added to water. Well, this is a metal oxide, and if you go back up in the notes, metal oxide and water forms a hydroxide. Now, potassium hydroxide looks like this, as separate ions. So it's best to show it separate, as opposed to that. Although that's not really wrong, what I just did in green, it's just not as clear. All right, copper 2 chloride solution, so write them separate, copper 2 chloride, aluminum metal. Often when you're given two reactants that have metals, one of your first thoughts should be redox. And in this case, it is. The copper gets reduced to copper metal. The aluminum gets oxidized to an ion that's now soluble. We have things changing state, so it's best to show the states. You don't have to show the states, but I recommend it. It's a good chance you might want to go back to the reduction chart from last unit on page 481. It can be helpful here. For example, if you look at the chart and you look at your voltages, you'll see that this reaction does happen between the copper and the aluminum. But the reaction between, let's see, what else could we do here? Well, we can't give electrons to aluminum. And if aluminum gives electrons to chlorine, we can't do that. If you thought, well, maybe my copper 2 chloride will react with itself, Well, if you look on the reduction chart, that won't happen. You'll see it's a negative voltage. And also, if that was the case, why is the aluminum metal being added? So that's how you can narrow that one down. You probably don't know what acetylene is, so it says ethyne. We'll go through how to figure out the formula of ethyne in the next lesson. So I'm kind of jumping ahead a little bit right here, but that's C2H2. It's got a triple bond, like this. And then a hydrogen sticking off each side, something like that. And it's exposed to concentrated chlorine. And so what happens is, this is an addition reaction. And notice I went ahead and did it twice. If it had said something like diluted chlorine or something like that, I would have only put one Cl2 pair onto it and kept the double bond that remained. But this is something we'll practice in the reactions as we go through it. Because it says concentrated, you want to take the reaction as far forwards as possible. So what happens is one of these extra bonds goes like this, which allows you to attach two chlorine atoms from one Cl2 molecule. And then you still have an extra bond, so you can take the other bond and then attach another pair of chlorine atoms. So that's what I did here. Ammonium carbonate is heated, so this follows the heated section. It also follows the fact that when you have one reactant, it's often decomposition. And when you do something like this, you might be thinking, well, I don't know what the heck ammonium carbonate turns into. Just turn it into stuff you've heard of. There's carbon and oxygen, so carbon dioxide. There's hydrogen and oxygen, so water. And there's nitrogen and hydrogen, so ammonia. So just turn it into stuff you've seen. Take a guess. If you can make something you've heard of before, do that as opposed to creating brand new molecules and things that don't exist. All right, last thing. Complex ion stuff. We'll talk about the demo later on, so don't worry about that right now. Silver nitrate solution, okay, silver nitrate solution is mixed with ammonium hydroxide. Well, what's interesting here, and I'm going to show this, is when I first mix this with ammonium hydroxide, we actually get a precipitate reaction between the silver and the hydroxide, which forms this, and I'll show you. Then, if I add more ammonium hydroxide, the AgOH precipitate that I had up here, the hydroxide gets pushed off and the extra ammonia becomes a ligand, and I doubled the ligands because it's Ag+1. So I did 2 ammonia ligands forming this complex ion. And here's the hydroxide that got pushed off. Now, one thing that's going to get you right here is you might say, oh, silver nitrate, ammonium hydroxide. I gotcha. Okay, that makes sense. They're both there. And you might be thinking, where did the ammonia come from? Well, it turns out something that we're going to need to be aware of is ammonium hydroxide solutions are always in equilibrium with ammonia and water. So when I do this demonstration, this is one chemical. It's the same thing. They're just in equilibrium with each other. I'll show you when we get there. Here's another one that I'll do. It's a very similar demonstration, but instead of using a silver solution, which, like I mentioned here, forms an ugly precipitate, I will use a copper, which will form a pretty precipitate, and then a really cool blue solution at the end. And we'll talk about that one in more detail when I do the demo. Do recognize here, though, that the first step, I make a precipitate. The second step, I make a complex ion. You don't have to do it that way. It's just an example that I like to show. And we'll do some other versions later on. Regarding the homework, I normally tell people to review their first year organic notes because of the next lesson, but I think a lot of people last year, because of COVID, didn't do organic chemistry. So if you did organic, go ahead and review your notes, but if you didn't, don't worry about it. You'll just spend more time with the next lesson. And that should take care of this one.